and use our whiteboard to explain. I am used to repeat the main teachings, the main issues or topics of the previous lesson. So what we learned in the previous lesson is to calculate the confidence interval of the mean. That is a mathematical object like this, an average value plus minus an absolute error with a probability p, and the probability is called confidence level. We are talking about making replicate measurements of the same direct measurement. So we have collected x1, the first result, x2, the second result, xi, the generic result, and xn, the last result. And we said that for now, we are computing only the statistical errors, so the one that lays when we replicate a measurement, because due to the uncertainty of random replicating, we will observe in general different results for the same measurement. So we said that the statistical error can be written like this. Delta is equal to a statistical parameter, t of student, which accounts for the significance, the risk of error that we accept, and the degrees of freedom. That is the difference between the number of measurements and the number of parameters to be calculated. And this t must be multiplied by the standard deviation of the problem. Our problem is calculating the confidence interval of the mean, because we want to predict the mean of a new series of n measurements. So we write like this: standard deviation of the mean, and we know that the standard deviation of the mean is equal to the standard deviation of the single measurement divided by the square root of the number of measurements. So this is what we learned in the previous lesson. And I said the analytical chemist is interested only in the confidence interval of the mean, because in every experiment the same measurement is always replicated, and we want to predict the average of this replicated measurement. So we call this confidence interval of the mean. Okay, this is all we have learned. We have also talked about significant digits, because we said when I perform a measurement, I obtain in general an error with many digits, but not all of them are meaningful. Not all of them carry some experimental information, because some of them come from calculations. So we said that, for instance, if we have a result like this, a result like this, 0.00897. This is the result for the mean. And we have obtained an error like 0.0001927, etc. we are looking to the error, this number, and we reflect on the fact that the order of magnitude of my uncertainty is this position. And this position is 10 to the power minus 4. So I am reflecting that all the digits which are below this order of magnitude cannot be quantified in a meaningful way. So the digits that I delete in red are not significant. They do not carry information. They come from calculations. So I need to round this error. This error should be rounded with only one significant digit. And in order to count the significant digits, it is useful to write the number in the scientific format, because I know that the correct way is a natural number from 1 to 9 multiplied by an exponent of 10. So I can write this. Okay, when I round this number, I have a 9 here, so the previous digit should be increased of 1. So I will write the result: 2 multiplied 10 to the minus 4, or 0.0002. This is the correct way of visualizing that number. Since I am making errors on this order of magnitude, this one, I can consider significant only the digits in the mean value which have an order of magnitude equal to 10 to the minus 4 or higher. So this is 10 to 0. 10 to 0 is higher than 10 to the minus 4. So this is significant. This is okay. This is 10 to the minus 1. It is higher than 10 to the minus 4. It is significant. This is 10 to the minus 2, significant. Minus 3, significant. Minus 4, the last. This is not significant. So I have to round this number to the power corresponding to the digit 9. And I can write it in two ways. 89 becomes 90. So 0.0090 or 9.0 multiplied 10 to the minus 3. Okay? Look, this 0 is significant. For a mathematician, it doesn't make sense. For a mathematician, 9.0 is equal to 9. But for me, this is informing that the precision of my measurement is there on 10 to the minus 4. Okay? Good. Now we go on, and we want to do an operation that the analytical chemists call validation. The question is this. Okay, you have measured 9 values for x. You have measured x1, xi, xn. You have obtained an experimental result, that is the confidence interval of the mean. So you have obtained this interval, x average plus minus t depending on alpha and e, multiplied sx over square root of n. But is it correct? We mean the true value really falls inside this interval? Because if the true value falls inside, we are correct. If it falls outside, we are not. Okay? Is it clear for you? Okay, so we can say, well, it is easy to compare the expected value with the experimental value. For instance, if I obtain 2.34 plus minus 4.04, is it a number like 2.31 inside? I mean, if the expected value were 2.31, am I correct from the experimental point of view? Yes, I am, because this interval goes from 2.30 and 2.38. So 2.32 is inside. Okay? Okay, and if the expected value were 2.38, I don't know. Is it inside? Is it outside? It is on the border. So I cannot decide. In order to take a decision every time, I use a statistical procedure that is called significance test. There are many kinds of significance tests, but the first that we are facing is the t-test. First test, t-test. Now I will give you some definition. I can ask you at the exam, what is a significance test? And the answer is, a significance test is a statistical procedure aiming to compare an experimental value with an expected value, or two experimental values with each other. And the problem that I propose to you,
can I repeat, please?
Okay.
Thanks.
Significance test is a statistical procedure to compare an experimental result with an expected result, or to compare two different experimental results with each other. The case that I proposed you here was to compare a number, the expected value, with the confidence interval. So the first case, to compare an experimental output with an expected one.
I'm sorry, Professor, because in my opinion, the experimental value is the one I really measure, or...
Yeah. The experimental value is the one coming from measurements and the data processing.
Okay, so in that case, 2.38 is the value I measure.
Yeah.
So it's the experimental. So in that case, I compare the experimental to the expected.
To the expected, yes. In this case, this is the experimental. Experimental. This is what I have found by measuring. This is experimental. I have measured. I will try to explain with an example. The example of the pipette. Okay? You take a pipette and you read on the pipette 15 microliters. This is the expected. Okay? Because it is written on the tool. The expected. I take the pipette, I fill with water, I weigh the water, I calculate the volume, I calculate the volume many times, and from these many measurements of the volume, I obtain the experimental result. This is the experimental result. While the number that I read on the pipette is the expected. It is not clear?
The expected depends on what?
The expected is readable somewhere. In the example that I have given to you, the very simple, measuring the volume of a pipette, it is written on the pipette. Okay? In general, when I want to calculate a concentration of a certain analyte in a certain matrix, I need to have some certificated reference standard. This is how a chemist proceeds. For instance, okay, the simple example was the pipette, direct measurement. Okay, I read the expected value of the pipette. I will write, for instance, pipette, and on the pipette there is written 500 microliters. I take it, I measure the volume, say 10 times, and I calculate the average plus minus T corresponding to alpha, 9 degrees of freedom, multiplied the standard deviation of the volume divided by the square root of 10. If I have made 1, 10 measurements. Okay. In green, I have written the experimental values.
So we want to understand if the experimental value is correct?
Yeah, we wanted to understand whether the experimental result, the confidence interval of the mean, is correct. Does it correctly predict the expected value? Okay? This is the 500 microliters in this example is the expected value because it is written on the pipette. Is it true? I take the pipette, I read 500. Is it true? I want to measure. I measure 10 times and I calculate my estimation of the volume. And my estimation of the volume is this interval. This is my estimation of X. Estimation that is experimental. Okay? Is it clear for you? In general, if I want to quantify how much copper is in this water, what do I need? I purchase a certificated standard of copper with an accurate concentration in water. And I measure that standard. I measure the standard. I need to find an experimental result which is, we say, not significantly different. Okay? In the case of the pipette, we need to demonstrate that our confidence interval in green is not significantly different with respect to the expected value. So we need to verify whether it is inside. But in order to make the procedure a mathematical procedure, not I say in Italian geometric, that is comparing two numbers by division. No, I want a mathematical statistical procedure which can compare the expected one with the experimental result. Okay? So we study now the t-test in this way. Okay, my experimental results are belonging to a Gaussian distribution. I plot this Gaussian distribution, that is the population to which my sample belongs. Remember that these values, x1, xi, x10, are a statistical sample of all the possible measurements that are the population, the statistical population. So I plot the statistical population. We know how to do it. Horizontal axis with all the possible output of the measurement of x, a vertical axis with the probability to find those values of x, and a bell-shaped curve that is the Gaussian distribution. Okay, my way of reasoning is this. I put on the x-axis the borders of my confidence interval. Okay? So the borders of my confidence interval are on the right, x average plus t. This t, alpha, depends on alpha and n, and is multiplied by Sx divided by square root of n. And for easy comprehension of the problem, I rename T, alpha n. I call it T tabulated. T tabulated comes from the statistical tables from which the function of Excel in .t on .2t calculates this T. You remember? We calculated by a function of Excel that was t.end.tt. This was the function of Excel used to calculate this t-tab. Okay? And on the left, of course, symmetrically, I have x average minus t-tab multiplied as x divided by square root of n. Okay? Now I put on the x-axis the expected value, and I call it xk, that is known, what I know, what is expected, what I know of that value, and I put it here. I plot a spike to make it more clear where x falls, xk, okay? So xk is here, And to better visualize it, I have plotted this spike. But it is here. Xk is here. Okay? Now I'm asking to you, is my confidence interval okay?
Yes.
Yes, it is, because it is inside the confidence interval. In order to make my observation mathematical or statistical process, I rewrite xk. And I write it like this, and then I will explain. So I rewrite it as x average plus t observed plus, multiply sx divided by square root of n. Maybe it is easier to use another way to indicate it, because last year it was a bit confusing. Tk, okay? Tk is that value of t which corresponds to xk. This procedure is changing the variable. That is, instead of speaking about xk, I speak about the value of t which corresponds to xk. You know, in this distribution, if I start from x average, that is the maximum, and I move right, I am finding several values of x, and each of them corresponds to one single value of t. There is a biunequivocal correspondence between the values of x and the values of t. I know that it is not enough, this explanation, so I will rewrite this red text in another way. So I will calculate tk from this equation. So I will type there that tk, tk is equal to xk minus x average divided by tk multiplied sx divided by square root of n. Do you agree that it is the same? Writing this equation 1 and equation 2 are the same. Do you agree? I have calculated the tk from equation 1 as a function of the other parameters. So you see that xk minus x average is equal to tk, etc. And then I divide it by this. So I have calculated tk as a function of the other parameters. Is it a problem?
It's not tk that is dividing. Should be there.
Sorry.
Okay.
Yeah, you're right. Okay, you're right. Okay. Now is it good? Okay. Now I have a look to this writing. What is xk minus x average? It is the distance. Okay. So the numerator of this in blue, this numerator, is this segment. Do you agree? Okay? So I have considering the distance. But I'm not measuring the distance with the unit of measurement of x. Suppose that x is in milliliters, just to fix the ideas. X is measured in milliliters. So x average minus xk is milliliters. I have divided by the standard deviation of the mean, which is in milliliters. 2. Okay? So T is a number without unit of measurement, a pure number. And this TK is answering to this question. At how many standard deviation of the mean is xk distant from x average? At how many standard deviation of the mean is xk positioned with respect to x average? How many standard deviation of the mean? This is the standard deviation of the mean. This is the standard deviation of the mean, okay? And I have used this standard deviation as unit of measurement of that distance. Suppose that Sx is this segment. I want to use another color to better explain. So I will write it in green. So this is standard deviation of the mean. Suppose that it is this segment. Okay? As standard deviation of the mean is the green segment. I take it as a unit of measurement. And I calculate how many times the standard deviation of the mean is inside of the distance.
The blue one.
Sorry?
So
the blue one. The blue one is the distance. Xk minus x average in blue is the distance. The segment is in green is the standard deviation of the mean. And I calculate how many times I can put the green segment inside the blue one. This is a way of measuring the distance in an absolute way, without unit of measurement. Okay? Is it easy for you, or do you want me to repeat? Since the same distance as this segment in blue can be found also on the left, you agree? So a value of xk can fall with the same distance on the right or on the left. That's why I write this blue as an absolute value. I take the absolute value of the distance.
No, sorry, Professor, can you repeat this part?
Yes. This blue segment that I have plotted only on the right
yes.
can be plotted also on the left. I mean, there is a point on the left which is at the same distance. And also it corresponds to the case that the xk falls on the left.
But in the case it would be negative, right?
Yeah, that's why I take the absolute value. I take the absolute value. If xk falls on the left, I take the absolute value. Okay? So this is the case where xk falls here. If xk falls on the left or on the right at the speed blue distance, tk is the same.
Yes, but this value will be minus xk, right?
Yeah, it is xk with a negative value, yes. Okay. If here I read 0.3, here I read minus 0.3, because xk is a generic symbol. Xk can be negative. When I write x as the name of the axis x can be positive or negative with respect to x average. Okay? X can fall on the right or on the left. So the difference between x and x average can be positive or negative. I didn't say correctly before. It is not x that can be positive or negative. It is the difference with respect to x average. So x average is here in the center of the curve. If I go on the right, I find some values whose difference with respect to x average is positive. If I start from x average and go to the left, the difference between xk and x average is negative. So, what is your name?
Sarah.
Sarah,
Yes.
I did not answer correctly to your question. Because xk here and xk here, let us call it xk prime. Okay? They are positive because they are volumes. They are positive. What is different is that xk minus x average is positive. Xk first minus x average is negative. Okay. No?
No, because generally I always do the value minus the mean.
Yes, I am measuring a value, a volume.
A volume, yes.
A volume is a positive
Yes.
parameter. So, for instance, suppose that x average is 500.
Yes.
Xk on the right can be 510, and on the left can be 490.
Oh, yes, it can be.
Okay.
Okay.
It is the difference that.
Okay, I see it here. Okay. Okay, thank
So
you.
that quantity xk, the expected value, minus x average, that is the experimental value, can be positive or negative. That's why I take the absolute value. Okay, so in this writing, I rewrite this in green because this is coherent with what I said. So the standard deviation of the mean, I will rewrite in green as x divided by square root of n, and also x average because they are experimental values. This is x average. So x average is experimental. As x divided by square root of n is experimental. And also tk is experimental. Okay? Because it is what I have observed. I mean, tk corresponds to xk, but it is compared to my experimental values. Okay? Now I put you a simple question. Tk is corresponding to xk, and it is the objective position of xk.
So it is experimental.
What is experimental is the average value, x average, and the standard deviation of the mean. Tk comes from the expected value and it is to be compared to my experimental values. TK is corresponding to the expected values.
So it is expected,
Expected, yes.
Also decay.
Also decay, yes. So, let us compare in this situation where I say xk is not significantly different with respect to my experimental confidence interval. In this case, now I will write a t as t tab. Okay? Really, x average and also the other are in green, are all in green, but I wanted to keep your attention to t tabulated. Now we want to compare xk with x average through the comparison of tk with the t tabulated. I mean, if xk is lower than x average plus t tabulated multiplied sx over square root of n, what is the relationship between tk and t tab? Now I repeat the question and try to simplify. Okay, let us give a name to the right border of the interval. X average plus t tab multiplied sx over square root of n. Let us call it x right, the right border. Okay? This is the right border of the confidence interval. I have given a name to simplify the reasoning. Okay? Simply a name. This number, x average plus t multiplied s over square root of n, I call it xr, the right border, or RB, right border. Okay? Simply assigning a name to this number. Is it clear, Sam? Is it clear? I give a name to this number. Okay? This is called for me x right border. Okay, if xk is lower than x right border, which is the relationship between tk and t tabulated?
Which is the relationship between
tk and t tabulated. If xk is inside the interval, that is, if xk is lower than x right border, then tk is minor than t tabulated. Okay? Okay, I can rewrite that and explain again. I will write.
Oh, sorry, Prof. T tabulated is the T value that we choose in order to have the interval that we are interested
The T tabulated is the T that allows us to calculate the borders of the confidence interval.
Okay.
Yes. Now follow me with your eyes. You are comparing this xk with this. Okay? X right border. You are comparing this number with this. But they are written in the same way. X average plus some value of t multiplied with the standard deviation of the mean. So comparing xk with x right border is equivalent to comparing tk with the t tabulated. Okay? If you want, I can try to explain with the other words, still other words, because this is, I know that it is very theoretical, but when we will perform the exercise, maybe it will be more clear.
So TK will be lower than T-tab.
Exactly. So, the decision criterion is this. If TK is lower than T tabulated, then we have no significant difference between xk and the experimental result. This is what I have found. And one could ask me, excuse me, why you have complicated your life by that way? Because when we perform the calculations of TK and T-tab by a software, the software always takes a decision, always. Because in the software, these two numbers, TK and T-tab, have many digits, I think 15. And it is almost impossible to find two numbers with 15 digits identical. So there is always a decision from the software. That's why I use this t-test to state, to establish whether there is or not a difference, significant difference. Of course, if we have that TK is higher than T-tab, so there is significant difference. So if TK is higher than T tabulated, then X average is significantly different. Sorry. X average is significantly different from xk.
So, Professor, can you repeat please why we use this
Because when you write the result of your work in a paper, you use a limited number of digits. Let us go to the example. This. Okay. You use 0.0090 plus minus 0.002. So a limited number. In this case, the numbers, the significant digits are 2. But in the software, there are all these digits. They are all present in the software.
Okay.
So both TK and TTAB are represented as numbers with many digits. And it is almost impossible to find that those two numbers are identical with so many significant digits. It's almost impossible. I can make an example. Okay, an example. Suppose that we find TK equal to 2.197321897 and others. T-tab, T-tab, you can find 2.197, but 3, it is difficult. Okay, let us write 3, but then they will change. 10973. So a decision is taken. If I had visualized these two numbers with 3 digits, they are both 2.20, 2.20. They seem identical, but they are not. Okay, that's why. That's why I use this procedure. And another motivation of this choice is that comparing a confidence interval with a fixed number is easy. But we will study another problem where we compare two confidence intervals. So it will be not so easy to compare two intervals. Okay?
No.
Today,
No,
tomorrow.
Because I mean, I perform the test for comparing these two values.
Yeah. In this way. Through TK and TTAB.
Okay. But I understand that I have it is difficult to compare them because I have numbers with many digits.
The comparison between the two numbers will be performed by the software. Okay. So the software will tell me, using 15 digits, I see that TK is lower than or higher than. It is almost impossible to find TK and TTAB identical with 15 digits. It is almost so a decision is always taken. But this is only one reason of this proceeding, because in the next hour, after 15 minutes break, I will explain to you how to make an objective comparison, because you understand that when I compare this result, this experimental confidence interval with a number, the fact that the number falls inside depends on alpha. In fact, I will repeat in the next hour because it is not so immediately. I want to. Okay, let us have a look to this plot. X right border is this point because I decided how much area leaving on the right. It is alpha. I decided. Alpha is quantified by this area. Alpha divided by 2, alpha divided by 2. This is alpha 2. It is me who decide. Suppose that I increase alpha. I want. So the borders will be closer, and there is a point where xk is out. The fact that xk is inside or out depends on alpha. So it is a subjective decision. This is a subjective decision. Depends on alpha. Depends on, I'm tired, I need a coffee. On alpha. I want to take a decision which does not depend on alpha. And I can do it only through tk. Okay? I will explain it the next lesson, the next hour, after 15 minutes break. Okay? Okay, we start the recording. Okay, we learned that we can compare a confidence interval of the mean, that is an experimental output, with a single reference value, which is the expected one. And we obtained this kind of conclusion. Okay, if you want to compare the two values, ask Excel to compare the value of t that corresponds to the known value, okay, with the value of t that you have used to calculate the boundaries of the confidence interval. Okay, but this depends on alpha. And it is not easy to explain to non-scientific people that my decision is not general. It depends. I cannot say to a lawyer, okay, or a judge, I cannot say, okay, if you choose 5%, it is not different. If you choose 10%, it is different. It is astonishing. Okay. I should give to this person an easy, objective criterion of how much xk gets close to x average. Okay? So now I will draw again our problem, but I will draw only the Gaussian distribution and xk. I will not draw the boundaries of any confidence interval. So here I put all the possible output numbers for x. Here the probability that I can read this result. And the statistical population that is identified by X average. And
Sorry, but just to know if I understood you well, this should be S average of S average, right?
Yes, this is the central point of my confidence interval, the average. Simply said, X average is the sum of all the Xi values divided by the number. This is X average.
Yes.
Okay. So if I have measured the numbers x1, xi, xn, I know that their average is a good estimation of the point of maximum of the population. Okay? Is it clear for you up to now? Now I draw the expected value. It is here. This is the known value, the expected value. Is it good? In order to answer, can I delete this? They are already listed. Now I consider another case. The same population as the upper one. They are different, but they are the same. I have drawn different, but they are the same population. Here there is always X average, and Xk falls here. Case 1, case 2. Or operator 1, operator 2. Who is better?
Good operator.
The second. The second is better. Why?
Because it finds a value that is closer to the average.
Exactly. Xk is closer to X average. Can you find in these two plots an area that is quantifying how close the two values are? Meanwhile, I will change color to use always the same. Is there an area in these plots that can account for the closeness of Xk to X average?
Yes.
Which one?
The one in between
Yeah.
below
Between
the
or?
Oh yes, also outside.
Or outside.
Okay.
The tail. This tail. This tail. The second result is better because the tail is higher. Okay? This tail is called p-value. And it is the objective number that we use to quantify the closeness of Xk to X average. Do you agree that p-value does not depend on any of our choices? It is there. It is not me that put Xk there. It is there. And this p-value ranges between which extreme values? I will repeat the question in the two possible extreme cases. When Xk is extremely far very far from its average. How much is p-value? To infinity. Scale is to infinity. Infinitely distant. How much is p-value? 0. Now, we have to, in order to make the second question, the second extreme case, we have to focus that p-value is two-tailed, because if sk is here, there is a symmetric point here at the same distance. So we are computing p-value in a two-tailed manner. This is the two-tailed. Okay? Remember that the area below the curve from minus infinity to plus infinity is 1. 100% probability to find a number between minus infinity and plus infinity. Second question, what does it happen when xk is identical to x average? How much is p-value? 1. So, we have found that for the t-test, p-value ranges from 0 to 1. This is a degree of similarity. This is a degree of similarity. And if p-value is 0, means that x average totally different with respect to x and if p-value is 1, means that x average is identical to xn. Okay? So, how can we calculate the p-value? We will do it in the afternoon together with Excel. It is enough to communicate to Excel the tk corresponding to xk. Okay? We will do that. Because we have, where can I write it? We have that tk is equal to the absolute difference between x average and possible comparison. Absolute difference between x average and x known, xk, divided by sx divided by square root of n. Okay? So, we can ask to the software, which is the area in the two tails when tk is this value? Now, I will try to explain why should we use this TK? Why cannot we simply compare the two numbers? And I will explain this by an example that I did with you. Yes?
Also, Professor, just clarification, because in the last formula, the subtraction between x average and xk is inverted. But it doesn't matter.
It is the same because
the
the absolute value.
I wanted to be sure. Okay.
You can write it like this, we can write.
Okay.
Or you can write like this, it is the same.
Okay, yeah, I just wanted to be sure.
Yeah. And we can also write it like this. Do you agree? This, as x divided by square root of n, is the standard deviation of the mean. And x, k, can be written on the left or on the right. It is the same because we have the absolute value. Okay? So, I discussed with your classmate before. Why? Why using this? It is boring. Why do I have to perform all these calculations? Okay, now I propose to you this problem. Sarah?
Yes.
Measured. It is not called Sarah. Measured a volume. And she found 103 plus minus 3 microliters. And you, your name? Julia? Julia? Measure a density, and she found 0.97 plus minus 4.03 grams per milliliter. Okay? Who is better? I cannot answer. Cannot answer because the difference of Sarah is 3 microliters and the difference of Julia is 0. Of course there is information missing. This expected was 100 and this expected was 1. Okay? So Sarah is distant 3 microliters, okay? Because I am comparing the average. And Julia is distant 0.03 gram per milliliters. I cannot decide because they are different. But I can give the value of T for Sarah and the value of TK for Sarah and TK for Julia. Now I must invent some numbers because I cannot calculate exactly, but suppose that Sarah has a TK of 4.8 and Julia has a TK of 2.10.
And the p-value?
And the p-value, suppose that the p-value is 0.9, this is invented. These are invented values. And this, maybe we can write only the p-value, simply. Because the p-value is calculated from TK. We will see in the exercise. So suppose that the p-value for Sarah was 0.9 and p-value for Julia was 0.8. Who is better? Sarah. Sarah has got closer to the expected value. There is a possible direct comparison between operators measuring different parameters. So the p-value is general. Now, this criterion that I have written in this slide is objective, because I am measuring the degree of similarity. And I know that it can go from 0 to 1. I think that every person, even with no scientific culture, can understand when I am good or I am not. The closer I get to 1, the better I am in evaluating the closeness of the expected value with respect to the average value. Do you agree? It is easier to understand. Now, in general, the students put to me a question. Which is the sufficient value of p-value? How much should it be, p-value? No answer. It depends on the problem. It depends on the consequences of stating that they are similar or not. But there is an empirical rule for the chemical analyst. And the empirical rule is this. So we state this is objective. And the empirical rule will be written here. Empirical rule for analytical chemists. And the rule is, if p-value is at least 0.3, sufficient. If p-value is higher than 0.7, good. If p-value is higher than 0.9, excellent. Okay, this is an empirical value, good. And it depends, the subjective decision is very much depending on the kind of problem. For instance, if finding xk close to x average allows us not to condemn a person, we need it very hard. But if the decision is whether spectroscopy is better than gas chromatography for a certain measurement, okay, it is enough for me at value of 0.3. I mean, when the consequence of my objective decision is very strong, In that case, I claim for excellent similarity. Excellent. And it should be excellent similarity. And we will see that the analytical chemist wants an excellent similarity in some cases. And I will show it to you when we want a similarity very high. Okay?
Sorry, I didn't understand the comparison between EUV and the chromatography.
When you are comparing the performance of two instruments and you find that both of them give a p-value at least of 0.3, you say, okay, it's enough for me, because 0.3 is higher than the minimum significance. But if I want to demonstrate that that a pipette is very good, I want a very high p-value. Because if on the pipette there is written 500 and I use that number for further calculations, I need that it is very close to the true value. Otherwise I will make strong errors. I think that there is something missing for our reasoning to answer your question, because I wanted to focus to another question, another issue. This is what you are reading now, an objective evaluation. But we can use p-value also for a subjective evaluation. And I will show to you how. I will. Okay. So have a look again to this plot. We have drawn alpha in green. Alpha in green is the level of risk that we accept. Okay? While p-value, in this case I draw it in red, is all this tail. Okay? Which is the, so in red we have p-value. Which is the relationship between p-value and alpha when I say there is no significant difference. And I say no significant difference when tk is less than t tab. And which is the relationship between p-value and alpha when tk is minor than t tab? Have a look. Sorry. Okay. In this case, tk is less than t tab and p-value is higher than alpha. Okay? It's the same. So, writing tk minor than t tab is equivalent to writing p-value higher than alpha. How can I read this writing? When the degree of similarity, p-value, is higher than the level of risk that I accept, I conclude, okay, no significant difference. Okay? I will write it. So p-value higher than alpha. And here, p-value lower than alpha. Okay? Is it clear for you? In general, statisticians choose alpha as 5%. This is a general choice because the statistician decides that when some event occurs less than 1 times over 20, that is 5%, it is random. This is one. So, if alpha, the significance level is 5%, that is 0.05, you see that in this empirical rule, 0.3 is 6 times the minimum level of similarity. Okay? 0.3 compared to 0.05 is 6 times higher. So we chemists say it is enough for us. Of course, if it is still higher, better. Okay, that's why we say 0.3 is not so low with respect to the general level of risk accepted. I will write it here. General alpha accepted is 0.05. This is a good explanation of this empirical rule. Okay. So, in general, when the degree of similarity is enough for us, we say, okay, we can consider that the two measurements are not significantly different. Otherwise, they are. Okay, is it good for you? Okay, now we can stop the theoretical lesson, and at 2 p.m. we will start with the exercise. I have modified the exercise in virtual because I changed the same symbols as in the lesson. So in the afternoon you will download that file, or if you want you can download it now, and we will start in the afternoon as you want.